Welcome to another data science deep dive on our technical track. In the following session, we have John Peach, Senior Data Scientist at Amazon Alexa, and he's going to be talking about literate statistical programming. Science is facing a crisis around reproducibility, and data science is definitely not immune. Literate statistical programming is a workflow that binds the code used in analysis to the interpretation of the results. So please watch this session to learn more.
So I want to talk to you about literate statistical programming, and I'll talk to you a little bit about that, what it is. It's been sort of a popular trend, and it's largely been talking about doing reproducible research, because you all know we have a bit of a problem in science with reproducibility. But I think that this solves a whole bunch of other problems too, and that's what I want to sort of talk about. So we have a problem of reproducibility in science, and so we're going to talk about that very briefly. Then we'll talk about what is literate programming, and then what is literate statistical programming. Literate statistical programming comes out of this software development concept of literate programming. And then we'll talk about problems with the status quo of how we do science and how we do reproducible research. And then we'll talk about how literate statistical programming can solve some of those problems for us. So replication is the core of science, right? If we can't replicate our research, then we actually really don't know how valid that solution is that we have, right? The whole basis of p-values is that some of the time we're wrong. And so we want to replicate things. It's also difficult to get funding for doing replication research. Funding agencies don't want to fund it, and publishers don't want to generally publish. My wife and I, we publish together. She's a researcher at UCI, and she has an amazing paper that's better than a paper that came out 6 months before hers, and she can't get it in the really top journal. She's had to go down a few tiers just because it's already known information. So there's sort of this devaluing of reproducibility. And it's often not technically possible to replicate the studies. It's expensive, you don't have access to the right equipment, the right skill set, and stuff like that. And so some of the problems around reproducibility is that we have very inadequate tooling. We don't have good tools to do this, and what I'm trying to pass on to you is let's develop a bit of a movement to get literate statistical programming into our common paths of the way we work, so that tool developers will go and build us great tools for this. And then we also have a training problem, right? Everybody comes out with a new tool, and then everybody has to learn it and stuff like that. So what are some of the ways that we can avoid having to reinvent the wheel? So the tooling problem. So the way science is done is not in a linear process, but a lot of the tooling, like if you look at Jupyter notebooks where you have your code and your comments, they're designed for this this linear process. But basically, there's sort of 5 stages to the way we do science. And one is we empathize with the customer or the problem. We define the problem in a very clear statistical way. We ideate, we think about how we're going to solve it. We build a prototype, and then we test. And that's the linear process, and that never happens, right? There's always these circling back and forth. You think about the problem, and you're like, oh, I didn't quite define that quite well, and you go back and you redefine it, and you build a prototype, and okay, that doesn't quite work, and you go back and you redefine the problem again, and then you ideate on it. So we need tooling that handles that nonlinear workflow process, and we don't really have that. So the solution is we're going to need to build tooling around literate statistical programming, but as a community we have to start doing this as a normal part of our workflow. So what is literate statistical programming? It's a single stream of human readable text and machine code together. So you have your text for the report you're going to produce and your code side by side. And there's 2 sort of concepts. There's the weaving and the tangling. So weaving says I have this one document, and I'm going to weave the process, and the output is going to be human readable text. And then I'm going to tangle it, and I'm now going to get executable code. But they're from the same document. It's not that I have a text document and a code document, that they're one and the same, and then I'll weave and tangle them to get those separate documents. But I only really work on the one main document. So it comes out of, literate statistical program comes out of this concept of literate programming. And who here has heard of literate programming? No one. Wow. Okay, great. So literate programming addresses a problem that is developed in CS. So it used to be what's called the IBM approach. You would sit down for 2 years and you would write specification documentation, and then you would hand that over to the developers, and the developers would develop it. And then things would change. So Don Knuth, who's at Stanford in '84, he published the first paper about this. He's published actually 3 papers on it. The last one was in '92, where he proposed that we have machine-readable code and human-readable code side by side together, and we weave and we tangle them, so that when the developer writes their code, the documentation is sitting right there, and they can just go update the documentation. When they compile their code, they also update the documentation. So it's not some separate process. They're no longer decoupled. It's not like you write your code and then you send an email to the tech writer who then goes and updates it, and then you've updated your code and it's out of sync. So it's always in sync together. And that's the same type of approach that I'm proposing that we do with literate statistical programming. So in literate statistical programming, here's an example. So on the top, we have these special markers, hash tick, and this is out of R. And there we have the documentation. So we define our parameters, we define what the function is, we give documentation titles, we give an example, and then sitting right below it is the code. So if I wanted to change the mean function, let's say I want to add a parameter that said drop all the values that are missing, right? I would just add that feature into my code, update the parameters in the documentation, and then when I weave and tangle, everything is updated and synced. So literate programming, to give you an example, so at the top, sorry that's a little hard to see, we have a code block that's basically going to run a t-test and set a beta value. And then below that is some code that has some text. And what I want you to notice there is that where it says the p-value was, I have some more code. I don't hard code in what the p-value was, because as I change my data, I change my analysis, I clean things, my p-value is going to change. I don't want to have to go through my documentation and update it, right? I just want to compute this stuff on the fly. And what I have down below is the output. So the output is what would come out of the weaving process, where it would spit out what your p-value was, and it's computed in real time. Change your data, you don't need to update anything. It's computed for you. So this is an example of what a document would look like. So this is using R Markdown, but there's a bunch of other tools. I just tend to use R Markdown. So at the top we have some YAML that defines who the author is, the date, what the title is, and then I have a bunch of code, and then there is some text that's shown there that describes what's going on. So when you're doing your analysis, you're writing your code, you're going to, let's say, produce a graph. And then below that graph, you're going to write your observations about the graph. You'll never understand that graph as well as you do at the time that you're generating and thinking about it. The future you is going to come back and just look at that graph, but you're going to be missing context. And so what you want to do is write your notes associated with that graph right there. Later on, if you're looking at that graph going like, hey, that looks a little weird, you have your code and you can see exactly how that graph was produced. So what are some of the differences between literate programming and literate statistical programming? So in literate programming, the core thing that you're going to be outproducing is the code, right? Software developers are paid to write software, they're not paid to write documentation, and most of them hate doing it. And the documentation is optional. It should be there, but it's optional. In literate programming, right, we're trying to communicate our results. Like, I don't hand over reports that have code in it. Like, I don't even want to look at my code, let alone my boss, right? So the core thing that we're trying to do is communicate the results, but we need the code in order to sort of automate everything for us and to build out this pipeline. So it's sort of the flip, right? In literate programming, the primary output is the code. In literate statistical programming, the primary output is the communication. So what are the end products of literate statistical programming? So there's really sort of two things. One is the written report, and there's sort of two types of written reports. There's the consultant report, and I'll talk about that in a second, and institutional memory reports. And then we also have the model that we're going to output. So sometimes your output is just not a report that somebody's going to read. Sometimes your output is we want to make this model and move this into production, and the report is important, but it's secondary. What we don't want to do is decouple the model from the report and the model from the analysis. Those should be coupled together. They're always connected. And we want to save the pipeline. We don't want to save the output. And that's the key thing to take away from this. I'm saving how I generate the report or the model. I'm not necessarily saving the report or the model. At some point, you're going to save them and distribute them, but that's not the key thing that you're tracking. So the consultant style is your typical sort of consultant report. You have an introduction, a problem, what you did, your conclusion, right? It's think of it like a journal article or reports to clients. And for this, you shouldn't be having any code, but your entire report is generated from code. So this is where the weaving process comes in. You're not going to write your code and then write your report, because now you've decoupled them, you've broken it, right? So you're going to change your analysis. Now you have to go and update your report. We also have the institutional memory style reports, and these are usually ones where you don't have a well-defined definition of done, and you usually tend to have multiple people on it. So think of it, you have multiple people that are writing book chapters. It's one person is working on the theory, one person's working on an application, one person's working on an analysis. So you want to sort of have a mechanism where you can all work simultaneously together, but not step on each other. So think of it like a book of knowledge. And you'll often see this in universities where you have a lab working on a particular type of problem, or you'll see it in industry where you have a team working on different aspects of the same problem. And there's not like one output report. So the model workflow, so the output is going to be some sort of productionalized model. We're less focused on the documentation, but we want to have the production model not decoupled from the analysis that we did, right? If there's something failing in production or something going great in production, you want to be able to go back to what exact model, what data, what was it that you did in order to produce this. So the model is going to be tied to the analysis workflow, and this also allows us to make improvements easier. We can simply go in and say, okay, this model is doing poorly here. This is the exact code. I can go back to that version of the code and look at it, because by the time that you run your model in production, you've probably built other models. If you're one of these organizations that releases models very quickly, like Amazon tends to, then you release a model and it takes time to sort of bake that model and get results. And in the meantime, you've gone ahead and built out some other ideas. So what are some of the key issues that I think we can address with literate statistical programming, other than reproducibility, which reproducibility is a huge thing. So there's the fragmentation problem, the nonlinear workflow, rework of analysis, collaboration challenges, pipelining activities, and learning curves. And I'll talk about these a little bit more. So the fragmentation problem is that the code and the model are living in separate places. And we don't want them to do that. We don't want to have this model, oh, what was the code that went with that, right? We want those coupled together. We want to save that state as one unit. Unless they're truly coupled, we never actually really know what the end state is. And in my past, before I started doing this, I had all kinds of things that were like, I would do something else would do something, and we would like merge them back together, and we'd be stepping on each other, and we never really knew where we were. And like, he would delete my code, and I would delete his code, and stuff like that. So we want to avoid that. The other thing is we want to keep all the data in machine-readable files. So it's fine to put something in a notebook, but that information needs to get transferred to a machine-readable file. Everything's in the machine-readable file. Don't store information in file names, paths, People tend to do this, like, oh, this was this client in this directory. Like, it's fine to do that so that you can locate it, but that information needs to be in the actual file itself. So don't be parsing file names and files. And even if you're using manual notebooks, which I tend to do because I'm old, I still put all that information into a file. There's the problem of the nonlinear workflow that I mentioned before. We don't have this sort of like collect the data and then do the analysis and then we're done. Like science doesn't work that way. Analysis doesn't work that way. We have these highly nonlinear things. I want to try out this idea. It doesn't work. I want to keep that information around because like somebody may have a question like, hey, did you try out X? And I'd be like, yeah, here it is. But I don't want to like lose that, but I don't want to keep it in the main workflow. It didn't work out. So we should have this trunk, this central path that is the sort of the state of where we are today, what I've accepted as work. And then we want to be able to merge work back into that trunk as we find it useful. And then stuff that's not useful, we want to be able to keep that outside of the trunk, but still be able to locate it and look it up. Because we may decide like, oh, like, I thought about it this way and it didn't work out, but when I think about it this way, I'll just modify it and like maybe it works out and then I'll merge it back into the trunk. So we're not throwing stuff away. You're never like writing code and then deleting code. You're never writing comments and deleting comments. You always have everything that you've always done. There's the rework of the analysis. So analysis are never done once. Like so many times I've talked to people and like, oh, I'm just gonna do this quickly. I'm just gonna do it once. I've never done an analysis once. Almost every analysis I've done, I thought I'm going to do it once, but I've never actually done it once. So we want to have a workflow that allow us to rerun the entire analysis without having to do all the work again. So as the analysis grows, then we understand more. The more we understand, the deeper the analysis is going to be. And we want to rerun that analysis over and over again. We also may want to add in new data or remove data because we changed the experiment or changed the conditions or found there was a problem. So we don't want to have to go back and sort of explore all of that again and redo all our work. We want to automate that pipeline for us. So the other thing is that code acts as live regression tests. So regression testing is a CS concept where something was working and now it's not. That's called a regression. And we want to do the same type of things in our analysis. I showed that this was significant. I added more data. It no longer is. Right? You don't want to continue assuming that this was significant or it wasn't significant. Right? You always want to update and do your full analysis again, but you don't want to manually do your full analysis again. We also have a lot of collaborative challenges. So the data is located in different locations, in different formats. People do things differently. Like you'll say, okay, you get together as a team and say, this is the way we're going to do it, and then everybody does some slight variation off of that. You want to sort of standardize what people are doing. We also want to be able to control and audit everything that's done. We want to be able to say, Sally did this change and it worked or didn't work, and not to point fingers, but we need to be able to like, hey, why did you do that? And communicate what was not captured. We need to have mechanisms to prevent data loss, right? You're having multiple people working on the same thing at the same time. You don't want them collaborating each other, and by the very nature of collaborative work, you're going to collaborate each other. So we want to track all of that type of stuff. We also want to know what is the current state. We always want to know sort of like what we've all agreed on as the most recent version while we're off adding new things. We also want the ability to share with our collaborators. So one of the things that's popular now with journals is they want you to upload your code and ancillary figures and stuff like that, and which can be a huge amount of work. And what I do now is I do R packages. I just take the R package and upload it and I'm done. And we want to be able to manage parallel workflows. We want to be able to have multiple people doing things in parallel with each other and not necessarily having to communicate with each other about them. We want to pipeline our activities, but we want to pipeline what is reasonable, not everything. We don't want to prematurely pipeline things that you're just trying out. So go and fix your pain points so that you do have this end-to-end workflow. That's ultimately what you're trying to do, is like a one-button click and your whole analysis is done, including the report generation, stuff like that, we want to strive for no copying and pasting. If you ever find yourself copying and pasting, just stop and automate that. Copying and pasting is very prone to errors. It's not reproducible. We want to be able to remember one of our things was audit what we did. If you copy and paste, that's not getting audited. We want the ability to clean and visualize our data in a way that's automated. That's the bulk of what I do, and kind of my job is a data garbage man. And if I can automate that, that's great, because every time I add new data or redo my analysis, I don't want to repeat that very expensive operation over again. And I want the ability to do my statistics and my machine learning in the same place that I'm doing my data exploration. Right? I don't want to do data exploration and then go build my models. That's decoupling. I'm trying to not decouple everything. And because of this, we need sophisticated techniques for documentation. So who here has used Jupyter Notebooks? A decent number of you. So Jupyter Notebooks is great, except it doesn't allow you to write sophisticated math formulas or shift text boxes around and stuff like that. So you have your Jupyter Notebook and you can't go and publish that. I don't hand over Jupyter Notebooks to my boss and say, here's my analysis, right? He doesn't want to look at reams of code. It's not professional looking. So we want to have a tool that has advanced layout techniques like LaTeX and stuff like that. We also have a learning curve, right? At the end of the day, I don't want to be interrupted by my tooling. My tooling should be there to help me get my work done. I should have a very large community around my tooling. So let's use the existing tooling until we get sort of standardized toolings in the future. And so what we want to do is focus on what we have already in order to do literate statistical programming. Plus, each area of science does things differently. So I've changed different areas of science that I've worked in over the years, and it's a completely different sets of tooling. Like when I was in engineering, everybody used MATLAB. Now, the area that I work in, nobody uses MATLAB. So you need to have tooling that is customizable to each area. And things like Jupyter Notebooks and R Markdown and stuff like that are great. They allow you to use different languages. So how does literate statistical programming solve some of these problems? So right now, we don't have great solutions. So there's Knitr, which is in what's in our studio. It allows you to use a bunch of different languages. So you can use Python, R, C++, Bash, SQL, I think a couple of other languages. So that process is the process I use, and it's good because it supports multiple languages. Things like Jupyter Notebook supports different languages. It supports R and Python, which are the two big data science languages. However, it lacks a lot of the advanced formatting features. Each research project should be treated as a package. So you're going to basically create an isolated container that doesn't depend on anything else. You can have other packages, libraries that you've written that get tied in, but each analysis that you do is one package unto itself. And the approach I use is every analysis I do, I use Jira to track my workflow. So every package is a Jira ticket. And then I just use the Jira ticket as the name of the package. We want to use version controls to control all aspects. Remember, everything that we're working with is a text file of some form. Great for version control software, right? We're going to have a central trunk as for our main product line, and then we're going to do our work in progress using branching, and we're going to do our testing in there and stuff like that. And if it works out, we can move it into the main trunk. So that, I'm not looking at Fred's garbage and Fred isn't looking at my garbage. The finished product is what's in the trunk. We also want to use flexible standards. Don't write detailed standards, but use your code as standardizing things. And by this, let me give you an example to explain it. So if you have a driver or a configuration file that moves your pipeline and you say, okay, we want to add in another column of data because we think this piece of data is important, you put that into your code, that now goes into your driver file, and now you have a standardized way of reporting on the data. But it's flexible because I can add and remove things and I don't need to write a specification documentation. The specification is the code, and if it works in the code, that's good enough. All data sits in files. Remember, don't store information in file names and stuff like that. If you use a file name, this is client A's data, that's fine, but within the data file, it should also say client, this is client A. We want to write a report as the analysis is done. We don't do the analysis and write the report. As we're doing the analysis, we are writing the report. When the analysis is done, the report is done. We don't want to decouple these things. We don't want to have them be separate from each other. So this goes back to the concept of tangling and weaving. We want to tangle and weave as a part of our workflow. We want to build an analysis pipeline. So with every change that we make, change to the data, change to the analysis, we run the entire pipeline again so that we're updating everything and rechecking our results. You know, what was significant is not significant anymore. We want to know about this right away. We're going to use configuration files to manage the pipeline. So I call them generally driver files. Like, don't do read in this, everything in this directory. I say, here's a driver file that these are the files in this directory that I want to read in, because sometimes I might want to remove a file or something like that. All our work should be auditable, meaning we should be able to go back and if x is equal to 5, identify where that came from. We want to write unit tests on our data. If we're assuming that the data is normally distributed, we write a test that says this data is normally distributed, and when it's no longer normally distributed, the test fails so that we know, like, hey, if I'm doing a linear regression, I'm assuming my variables are independent and normally distributed. I want to know about that if it fails. And we want to dynamically create values, and this is going back to the p-value that I showed you before. No hard coding of any values. We also want the extensibilities. Like I said, every area of science is different, so we want tooling that is going to be extensible to work with the way that I work, not I have to work the way the tool works, or people just aren't going to use it. We want to wrap existing tooling to do the common things for us. We also want to have our tools be things that we know about, our Python, LaTeX, Git, that type of stuff. We don't want to go and reinvent the wheel. I'm not going to spend 6 months learning a new tool to do literate statistical programming, but I will spend a couple of weeks, you know, doing stuff in a literate statistical programming way using the tools that I know. So in summary, literate statistical programming helps us with reproducibility. That's key, but it does so much more. If you're making this argument to your team why you should be using literate statistical programming, that's the #1 thing you should be going after. But second to that, and still quite important, is it solves fragmentation problem, the nonlinear nature, reworking of analysis, collaboration challenges, pipelining our activity so that we're constantly redoing the analysis and then solving the learning curve problem. So thank you very much for listening to me. If you want to reach out to me, that's my LinkedIn address. I'm happy to connect with you on LinkedIn. I also run an R meetup in Orange County, which is the second line. We'd love to see you guys come out. And this weekend, we are having a data science hackathon. If you want to come to that, we have a few spots available. It should be a lot of fun. We ran the first one in May, and it was a huge success. So we think this one would be great, too. Thank you guys very much. Is there any questions?
This is from Monasi. She says, I work on model versioning. So thrilled to hear your talk. Since version control systems aren't queryable as a database, we have found the need to add a DB to make metadata easy to query. How do you handle this DB versus Git conundrum?
So I use other tools to basically act as the database. So like I said, every project that I work on, I have a Jira. So if you don't know what Jira is a common software development ticketing system. So I use that to find my work product, to see all the detailed documentation, like what I was supposed to do, and I use that as my search engine. As opposed to a database. But there's nothing wrong with using a database. It depends on sort of the workflow and the individual problems that you have. But yeah, there is that, the tools we have now is inadequate, and what you're just pointing out is this is another inadequacy of the tools that we have.
I have another question from Neil. This one went into DSSLA, so we don't see it on the screen, but Neil asks, Jupyter Notebooks let you add equations in MD cells using the $? Is there something else from LaTeX that he needs that Jupyter doesn't have? Oh,
so I didn't know about that, about Jupyter. Yeah, so if Jupyter is allowing you to use the $, that's basically pulling in LaTeX and you can write equations. Perfect, that's great.
That that was John Peach, Senior Data Scientist at Amazon Alexa. He described a workflow he successfully used in small-scale data sets on the Alexa size scale problems at his work at Alexa. He also covered tooling, workflows and more to master literate statistical programming, because he is definitely an expert in that. If you like this video and want to watch more, please subscribe to DSS Insider. You will find a link in the comments, and there you will find more content like this that you could watch on your own time. Thanks and enjoy!